Alright, so I want to start out by giving an overview of programming FPGAs and relate it to the hardware architecture and how it compares to a microprocessor, traditional CPU. I want to sort of format this as a programmer to programmer discussion. So if you're familiar with more along the lines of C or C++, then hopefully this will help. A lot of the differences come from the FPGA structure. Unlike a CPU that will read instructions from memory and fetch it, an FPGA really has registers with thin layers of combinational logic between them. You could sort of argue that the ALU is similar, but let's look at this by actually creating a project here. So we will go to new project next. I want to make a working directory. And we'll say FPGA intro. Select that folder, same thing. With the FPGA intro, we do not have any libraries. I have a Cyclone 3 board. FPGA 484, 6, and I have these 16. Don't need any of that, and we will hit finish. Let's see if we can see it in Chip Planner here. So this is the layout of an FPGA. You have different sections. The blue is what are called logic area blocks. If we zoom in here, there are 16 logic cells per logic area block, and I believe if we can double click this, should open, but it is not going to. So what the logic area blocks is these are these combinational logic and register parts. There's 16 logic area cells per logic area block, and that's what occupies most of the FPGA. The green are memory cells. These specifically are M9K blocks. They can be configured to different bit widths, and as suggested in their name, they have 9 kilobits of memory. Then we have a multiplier. These are the white cells. These are these are dedicated multipliers that can either multiply 2 signed 8-bit values or 1 signed 16-bit value. I'll cover that in a different video. So really, one of the major differences is FPGAs are programmed using hardware description languages, and I will give you a sense. We'll open a VHDL file. With hardware description language, what's commonly taught is that all your lines of code executes in parallel at once, and really the sequential sections, sequential being line by line is put into a process statement. That's fair, but it really doesn't give you the sort of depth of what's needed. C is a sequential language in which each line is executed one by one and sequentially down the page. But you know, the VHDL is not like that, even within the process statements. So let's start by creating a file, just creating a test run. And we will do, so first we will call our libraries. We need the IEEE library. This is a bug with Quartus here. There it is. And then library. We will do use. Out of this library we use standard logic 1164.all of it. And then I will also add use numeric standard.all. Excuse me. The standard logic library really defines the bit patterns, not only highs and lows, but stuff like unused or unknown or high impedance, just as a few examples. The numeric standard gives us signed and unsigned types and makes it much easier for doing math operations. So first, in VHDL, we have to describe what we're doing. So we are doing entity. I'll just do FPG intro because I misspelled without looking. Is port. We will put just A. We'll put A vect, which is standard logic. Alright, and then we'll have the vect. Sorry, we'll make them both vectors. And they will be 8 bits wide. I'm sorry, I can hear all my typing. I am not on a professional setup, if you couldn't tell, but thank you for bearing with me. And we will do the output. Vector. And for now, we'll do 7 down to 0. And then we will close this out, then end, and I always do entity. I will always make sure that we are, and that I'm specifically ending something. Now, architecture, the only reason I know how to spell that from doing this a lot, RTL of FPG is, I'm not going to have any intermediate signals, so I will just say begin. Now, here's a process. We literally started by saying process. And this process is going to look at A vect and B vect. And now we're going to describe our process. And we will just say A that our out vect becomes A vect or B vect. And process. Now I'm going to end my architecture. Alright, so I will save this as a VHDL file. We'll make this the top level entity, and we'll just analyze and synthesize. I'm not going to do well, I do need to do a full compile. That's okay, because there are errors, so let's fix these errors. Numeric standard. This is embarrassing because I'm probably just spelling it wrong. We're not going to use it right now. I do need to compile, so let's do this again. I know it's wrong because I don't usually use headers and not different things. You have to specify actually the library and then the section that you're doing. Here we go. Oh, can't write to outvect because I didn't actually specify these. Pure signal you don't need, but since this is part of the entry, we actually need to do this. Here we go. And we are compiling. Luckily it only takes a minute because we don't need to do a lot. It's not a big file. It's only like one register. So you can see we've used 8 logic registers. 24 pins, 8 times 3, correct. Not that this really matters because it's not actually going to go on a board. I'm not covering that. I just want to look at it, how it puts it onto the FPGA. So you can see that we've only got really one function here. You take these 8 bits, OR them, you output them. Let's look how this looks on our chip planner. And looks like they broke it up into a few places. Here is one place. Gosh. Okay, so what the analyzer did was it just put them all, it broke them apart and then auto-assigned pin values to them. Let me change my assignments here, and we will set all to virtual pins. From all to turn it on, and we'll recompile. We'll save the assignments and compile. See if that gives us a better chip planner view. Perfect. All right. Cool. A little bit better. So let's look at this. So basically, if we double click on it, we'll open our resource property editor. Now this is a single logic cell. And as you can see, it's just gone through the combinational of it. And it bypasses the register in the logic cell. I don't think that we can actually view what the logic is, and really I don't like this because I can't even see the input, probably because we are not actually assigning virtual pins. But still, we can see that I'm specifically looking at bit 5 of our two 8-bit vectors. This is only a vect. Let's see if we can trace where this is going out to. Let's look at this then. This is a lot better. So this is our actual combinational function. We can see that data A is connected in here and goes in. Here's data B. Data D is actually our B vect, so our signal A vect and B vect come in. And the combinational out is a sum equation of A and D. So essentially, if you remember from your classes, ORing is a sum equation. So that is pretty much what we want to look at. So your question is, well, we've written a lot of code here, essentially to OR two vectors together, when in C you could have done this in one line, and you are right. Unfortunately, that's one of the disadvantages, or one of the differences between C and HDL, is that you're really describing hardware, and this is another reason why there isn't a lot of good C to hardware description compilers on the market, or why there's not really a good indication of there's not really good solution for taking your C code and being able to really accelerate it effectively to be put it on the FPGA. That being said, though, the FPGAs are built for doing operations, as I showed earlier, a multiplication operation, but first let's look at a summing operation. So this is where I'll put in some signals. We'll put in signal a number, B number, and out number. And we're going to do these as unsigned, 7 down to 0. So this is another thing. Between the begin and end statements in our architecture, every line is getting executed simultaneously. That being said, it's much more easier to cast cast different signals that are not in a process. I will explain it by doing this. Basically, a num becomes a vect. So a vect turns into a num, but we'll just take the vector and do it as an unsigned value. Same with b. And then our out vect will become standard logic vector of out num. So I've assigned these, and in our process I will say, instead of ORing our vectors, we'll just get rid of this line altogether, and I will say a num, or no, out num becomes a num plus b num. Now there is actually a lot of unpacking that we need to do here. Older library versions, there's like a 1164 signed logic and 1164 unsigned logic. Those libraries are outdated and was replaced with this numeric standard library. The numeric standard library allows us to actually put in these unsigned and signed values, so it actually makes math a lot easier. So the reason I don't use signed and unsigned in my top level entries is for compatibility. As you start creating projects and they're getting a lot bigger, most of your entries still are defined as standard logic interconnections. A lot of your third-party IP is still standard logic interconnections. So it's much better to create these in standard logic than when you start using this design in others. You don't have to worry about compatibility. You can find other IP that say this port, whatever it is an 8-bit signed value, and it'll work. Or if you're interfacing from a microprocessor, the microprocessor is just going to spam out whatever it is, and it's much better. It makes compatibility a lot easier just to say there's a standard logic vector, and then in your component define unsigned or signed values. So we cast our inputs from our standard logic and then add them, and then change our unsigned value to an out vector. So let's compile this and see how many errors I have. None. I just forgot to change our process sensitivities. Not that that will mess us up in ModelSim, but not in Quartus here. So let's look at our values now. Much more defined here. And so let's look at this screen for a second and how it is. Fan out connections, sorry. Basically, to get the fan in. Okay. Well, anyways, basically what I've selected here is the fourth bit in an addition vector from the resource property editor. One thing I'd like to point out is, before we had a lot, they were very spread out. Here, they're not. They're pretty uniform in line. This is a pin input, but here is an addition, 0, 2, 4, 6, and what this is these logic elements are actually chained together to create an arithmetic operation. So this is much more efficient doing this in larger projects than trying to figure out your OR statements. They're built, basically what has happened is they've activated the carry in and carry out functions for additions. And so when you have statements where it's doing math, Quartus will actually change the utilization to try and fit whatever mathematical operations are being performed. That's pretty much all that I can see really defines this. The other point I would like to make is that these logic area blocks, the 16 logic elements, can be linked together to actually expand your vectors into 32-bit or 64-bit. So as you're coding, you really want to, and not only with FPGAs but with CPUs, you do really want to try and utilize the width of what you're doing. FPGAs, you're much more free to define your widths, but in CPU it's 8 bits, 16 bits, 32 bits. In a way, FPGAs are honestly the same because of the interconnections that are available. The Cyclone 3 series I have here is more geared towards 16-bit operations, but it handles 32 bits relatively easily. Let's go back here and let's get into the other part of the logic area blocks. The other thing is that the logic area blocks, if you want to utilize your logic area elements and create a very fast hardware design, you define operations of thin combinational logic between clocks. So let's put a clock in here. We'll put it in at the top. And so I've got the clock in standard logic, and what we'll do is we'll just add it into our process here. So we'll look at A num, B nums, and clocks. We'll begin, and if rising edge above the clock, then I did not do that. So what this statement says, so basically I'm putting in condition. If I'm looking at rising edge is a macro for event and then the output equaling 1. So if you have an event and the output of that event on your clock signal equals 1, then we will change outnum and we will perform our addition. So let's compile that, and we will take a look at our output. So here, now I can actually see where the logic is. 7, 6, 5, 4, 3, 2, 1, 0, going all the way up. So let's just look at one of these. So here you can see our input. We've got a lot of input here. We have our clocking signal input, and you can see clock signal there. We have A vect, B vect, we have our carry in from our previous signal, and then our combination out is the addition. So you can see that our addition will take place here, and then the data actually is stored bit by bit into these registers, and they are clocked. So really in a CPU, you talk about, they talk a lot about clock speeds. Intel processors have on the magnitude of gigahertz. More traditional and lower cost microprocessors are on the tens of megahertz or hundreds of megahertz, depending on how nice you get. FPGAs, you define the routing paths, the logic in them, and that in itself is the core of why CPUs and FPGAs are different. FPGAs, you can feed a lot of clock speed into them, but if you're doing microprocessor stuff, you can't really define that. Also, look at the architecture. I'm doing one operation, and it's happening every clock cycle. But if you really think about that and compare it to how many operations a program does in a CPU, all of this, basically the result of every line of CPU code and every bit, so if you have an integer that's 32 bits on your 32-bit microprocessor, that's going to fill up, 32 bits is 2 of these logic area cells, and that's going to fill this up fast. You can't do that, essentially. So the other point that sort of relates to is FPGAs are stream processors. You're going to get the most efficiency out of them when you're performing simple operations, but a lot of operations at a time. So they're best at working with simple instructions or single instruction, multiple data type operations. So filtering on an ADC, filtering video processes, signal identification and line or object detection. Those are processes that are going to be great for FPGAs if you can get the data out into a concise format that makes it easy to stream. So this is where I'm going to end this video. Basically, I hope that this helps you in sort of figuring out, you know, understanding the differences between FPGAs and microprocessors, especially if you're trying to get into more FPGA programming. We've made a simple file here with a simple operation, and what I'm looking forward to in the next few videos is getting more into defining how we interface between different modules, especially third-party modules like QSYS and the Neos processor, and also looking at how different resources, when typed out, different resources are allocated by Cordis and by the handler. Thank you so much for watching.